Hi and welcome to Unit 1, Topic 1, Video 3, where we begin looking at permutations, which is one of our two main features of this topic in Specialist Maths. So, let's have a look. I would encourage you to stop, pause the video and have a read through the learning goals, success criteria, and I'll leave that up to you now. So we need to start with an understanding of factorials. Factorial notation is used to represent a special type of calculation that is used a lot in the topic of combinations and permutations. So it's an exclamation mark. Now in that orange box there I've got n factorial equals n times n minus 1 times n minus 2 times ... times 2 times 1. So it's pretty spellbounding, that one there. But really factorials is pretty easy to understand when you break it down and have a closer look at the actual basic numerical examples. So here's an example here. 5 factorial, that's just equal to 5 times 4 times 3 times 2 times 1. So we just start at the number and then we multiply it by every single preceding whole number below it. 6 factorial will just be 6 times 5 factorial. Now there's an important note here in green. 0 factorial equals 1, which is really an important principle to make this theory and this concept hold together and to help us with proofs and other things later on. So let's start by evaluating 6 factorial. 6 factorial, of course, is equal to 6 times 5 times 4 times 3 times 2 times 1, which is 720. And if you have a look on your calculator, you should be able to find a factorial button, which will be an exclamation mark or a factorial key inside your functions or menu items. Now let's evaluate 9 factorial divided by 7 factorial. So I'm going to do this very quickly on my calculator and evaluate it numerically, and then I'm going to show you why that's really the wrong way or the long way to go about it. So first of all, I need to get my factorial key up here. I'm using a scientific calculator. I've got an X factorial key in the top right hand corner of my Casio. 9 factorial is equal to 362,880. Now I'll repeat this a few times. Factorials get quite large, so get used to that. 7 factorial is equal to 5040, and 9 factorial divided by 7 factorial, that number divided by this number is 72. Now 72 is a nice round number for this, and that's because actually I could do this. 9 factorial is 9 times 8 times 7 times 6 times ... all the way down to 1. 7 factorial is 7 times 6 times ... all the way down to 1, and of course they cancel out, and 9 times 8 is 72. So often you'll get this really nice cancelling out component. I could write 9 times 8 times 7 factorial over 7 factorial and just cancel those out. There's another way of looking at it. So here's another question, which I'm calling complex unfamiliar, to solve this equation. So we've taken a large step here, but let's see how we go, shall we? So firstly, n plus 1 factorial divided by n minus 3 factorial. So we'll zoom in this a little bit, and this gives us, and I'm going to write it out in full, n plus 1 times n minus 1 times n minus 2 times n minus 3, and I'm going to leave the n minus 3 in factorial form, over n minus 3 factorial. And that's equal to 18 times n minus 1 times n minus 2. And again, I'm going to do it in factorial form over n minus 2 factorial. So I know here that n minus 3 is less than n plus 1. And n minus 2 is less than n. So I know that there's going to be some nice cancelling out to take place. N minus 2 factorial and n minus 2 factorial cancel out. N minus 3 factorial and n minus 3 factorial cancel out. And I'm now left with n plus 1, n minus 1, n minus 2 is equal to 18 times n minus 1. Now, I can do some more cancelling out. N and n if I divide through, n minus 1 and n minus 1 if I divide through. Now, I have to be careful here and just make note that I've got n now doesn't equal 0 and n minus 1 doesn't equal 0 because I'm dividing by n and n minus 1. Now, I don't have to divide by n and n minus 1. I could solve this, which is a quartic, and may have 4 solutions. So I need to be careful because I may actually just be losing the solution n equals 0 and n equals 1. And in fact, if you have a look, that could well be the case. So I'm just going to be a bit careful and make sure that we come back and look at those. There's an important reason why those solutions won't work though, and we'll talk about that in a minute as well. And so we get n plus 1 times n minus 2 is equal to 18. And this is now a quadratic we need to solve. So I'm going to crack through solving it. I get n squared plus n minus 2n minus 2 equals 18, which of course is n squared minus n minus 20 equals 0. I've just subtracted 18 and brought the like terms together, which of course is n minus 5, n plus 4 equals 0, and n is equal to 5 or negative 4. And n could possibly equal 1 or 0 as well. So there's my options for solutions. I have to be careful. It might not equal this, but it could possibly equal that. But what I'm going to do now is have a look at what we know about factorials. So if we're talking about n factorial, well n, well actually maybe I should use a different letter, k factorial, k must be greater than 0 or equal to 0. We've got 0 factorial because 1 is by definition, but it can't be negative. So when I go back and have a look at this, my lowest possible factorial is n minus 3. So therefore n has to be greater than or equal to 3. So it can't be negative 4, it can't be 1, it can't be 0. So there's my solution. N equals 5. And if I want to test it, I can. And just a little test here gives me 6 factorial over 2 factorial. Is that equal to 18 times 5 factorial over 3 factorial? And I think if I run through that and check, I'll get 6 over 2 is equal to 18 over 6, and that's true, so it works. So there we have it. That's factorial notation and how we solve a pretty complex, unfamiliar factorial equation question. All the best.